let's talk about sentence transformers, a powerful family of models designed for text embeddings. This model family creates sentence-level embeddings, preserving the full meaning of a sentence rather than just individual words. Built on top of BERT, SentenceBERT, and other transformer architectures, it excels in tasks like text similarity, clustering, and retrieval. Here's what makes that family so powerful. Sentence transformers generate fixed-size embeddings for full sentence, not just words. Optimized for semantic similarity, make it useful for search, question answering, and summarization. Support fine-tuning for domain-specific applications, more efficient than standard BERT for sentence-level tasks. Sentence transformer embeddings range from 512 to 1024 dimensions, depending on the model's variant. They are game changers for NLP applications, whether you're working on search engines, chatbots, or AI-powered recommendations. This model helps AI truly understand language. BERT models, including SBERT and its variants, are not API-based by default. They are pre-trained models that need to be downloaded and run locally or deployed in an application. What is BERT? Bidirectional encoder representations from transformers, or shortly BERT, is a deep learning model developed by Google that understands the context of words in a sentence by processing text bidirectionally, making it powerful for NLP tasks. BERT reads left to right and right to left simultaneously, which helps to understand context better. How do sentence transformers work? Sentence transformers, like SBERT, are based on BERT, but are optimized for sentence-level embeddings by using Siamese or triplet network architectures, enabling more efficient handling of sentence pairs. Trained with contrastive learning, ensuring similar sentences have closer embeddings. They use tasks like natural language inference and semantic textual similarity to fine-tune. Output dense float-point vectors that capture semantic relationships between sentences, pre-trained on massive text datasets, and can be fine-tuned for specific NLP applications. Unlike traditional BERT, which requires expensive pairwise comparison, sentence transformers efficiently map sentences into a vector space for fast retrieval. BERT is great for token-level tasks, but inefficient for sentence comparison, since it requires comparing each pair. Sentence transformers map them into a shared embedding space for fast similarity search. SBERT is both a framework and a collection of pre-trained models specifically designed to create semantically meaningful sentence embeddings. Let's take a closer look at some models from the sentence transformers family, starting with SBERT. Introduced in 2019, SentenceBERT modifies BERT by employing a Siamese network structure, enabling it to derive semantically meaningful sentence embeddings. This approach significantly enhances performance in tasks requiring sentence similarity assessments. Key features: utilizes a Siamese network architecture, optimizes for semantic similarity tasks, reduces computational complexity compared to traditional BERT models. DistilBERT. A distilled version of BERT retains 95% of BERT's language understanding capabilities, while being 60% smaller and twice as faster. It's often used as a base for sentence embeddings due to its efficiency. Key features: smaller, lightweight, and faster than traditional BERT-based model. maintains high language comprehension, designed to balance efficiency and accuracy, suitable for applications requiring reduced computational resources like low resource systems, mobile apps, real-time text classifications, and others. It has 512 dimensions. A robustly optimized BERT approach, RoBERTa enhances BERT's training methodology by utilizing more data and larger batch sizes. It typically achieves higher accuracy, but at the cost of increased computational demands. RoBERTa is known for achieving superior performance on various NLP benchmarks. Key features: improved training techniques over BERT, excels in multiple NLP tasks like advanced semantic search, question answering, text clustering, paraphrase detection, and high-precision NLP apps like medical, financial report analysis, document retrieval and law, AI-driven research tools that require deep contextual comprehension. It has 1024 dimensions. MiniLM offers deep self-attention distillation to create a lightweight and efficient model, making it suitable for tasks where computational resources are limited. Key features: compact model size, efficient performance with reduced computational demands, maintains competitive accuracy in sentence embedding tasks, suitable for small websites or mobile applications with limited computational resources, low latency, real-time content moderation, offering AI-powered note-taking apps, voice-to-text processors, processing millions of short text queries in a real-time recommendation systems while keeping computational costs low. MiniLM has around 384 dimensions, but some variants have 512 dimensions. To better understand which model suits your use case, here is a detailed comparison and benchmarking table showing their strengths, trade-offs, and ideal applications. Distance metrics for sentence transformers. When working with sentence transformers, we need a way to compare sentence embeddings. Different similarity metrics help measure how close two sentence embeddings are in meaning. Primary similarity metrics. Cousin similarity. This is the most commonly used metric. It measures the semantic similarity between two embeddings by calculating the angle between them. A higher cousin similarity means the sentences are more related. Dot product. This metric computes similarity using vector multiplications. It's often used in retrieval systems and large-scale search applications. Let's discuss some alternative distance metrics. Euclidean distance measures the absolute difference between two embeddings, but it's less effective for sentence embeddings because it doesn't consider direction. Manhattan distance, used in some niche applications, but not commonly applied to sentence embeddings. Hamming distance. This metric is only used for binary embeddings, and it doesn't apply to sentence transformers. For most applications, cousin similarity and dot product are the best choices for comparing sentence transformer embeddings. They provide the most meaningful comparison in tasks like semantic search, clusterings, and retrieval. best use cases for sentence transformers. They power state-of-the-art NLP applications by enabling models to understand full sentences, not just individual words. Here are the top use cases where they really shine. Semantic search finds similar sentences, documents, or frequently asked questions with high precision, whether it's for knowledge bases, legal documents, or customer support. These techniques improve search results dramatically. Retrieval augmented generation. Sentence embeddings help fetch relevant context to improve large language model responses, making AI-generated answers more accurate and reliable. Text clustering and classification. Organize large volumes of text into meaningful groups, whether it's for news categorization, social media analysis, or content recommendations. Questions answering. Find the most relevant answer from a document, frequently asked questions systems, or knowledge base, making chatbots and virtual assistants smarter and more efficient. Paraphrase detection. Identify sentences that express the same meaning in different ways, useful for plagiarism detection, duplicate content removal, and text rephrasing tasks. Sentence transformers are revolutionizing NLP applications, making AI-driven search, retrieval, and text understanding more powerful than ever. Optimizations and considerations for sentence transformers. If you want to maximize performance, here are some key optimizations to consider when you work with sentence embeddings. How to improve retrieval accuracy. Fine-tune on domain-specific data. Training sentence transformers on custom datasets can significantly improve accuracy for specific tasks such as legal, medical, or technical applications. Use hybrid search. Combine keyword search with semantic embeddings to enhance relevance. This approach works great in search engines, document retrieval, and recommendation systems. Select the right model variant. Choose the best model based on your needs. For example, DistilBERT-based models, best for speed and efficiency. BERT-based models, a balanced option between speed and accuracy. RoBERTa-based models, the most accurate but requires more computation. Next, use efficient vector databases. To store and retrieve sentence embeddings efficiently, leverage tools like Weaviate, Pinecone, Qdrant, or Fierce for fast similarity searches. Fine-tune your model and using the right retrieval strategy can significantly enhance the performance of sentence transformers. Let's go over some trade-offs to consider when using sentence transformers. While they're highly effective, they also come with certain limitations. Computationally intensive for large datasets. Even though these models are optimized, they still require GPU acceleration for handling large-scale retrieval efficiently. Not ideal for token-level NLP tasks. Those models are designed for sentence-level understanding, meaning they are not suited for fine-grained word-level analysis, like name entity recognition or part-of-speech tagging. Storage and indexing considerations. When deploying at scale, you will need an optimized vector database like Fierce, Pinecone, or Qdrant to ensure fast retrieval and low storage overhead. Latency in some applications. While sentence transformers are much faster than BERT, some models, especially RoBERTa-based versions, can still be slower than lightweight alternatives, like MiniLM. Sentence transformers offer powerful sentence embeddings, but for large-scale applications, GPU acceleration and efficient vector indexing are essential. While these models are great for text embeddings, other alternatives might be better fit depending on your needs. For example, QHEREmbed, an API-based model that supports fine-tuning, great for cloud-based NLP applications. OpenAI Ada, a general-purpose embedding model hosted via API, offering high scalability and easy of use. Universal Sentence Encoder, Google-developed model optimized for fast and scalable sentence embeddings, available via TensorFlow Hub. InferSend, an LSTM-based model from Facebook AI, one of the earliest sentence embeddings approaches. If you need custom fine-tuning and high-accuracy text similarity, models from the sentence transformers family such as RoBERTa-based SBERT, DistilBERT, and MiniLM are the best choice. But if you prioritize API-based scalability and ease of use, alternatives like OpenAI Ada, QHEREmbed, or Universal Sentence Encoder might be a better fit. InferSend, while an earlier approach, can also be considered for certain LSTM-based applications. Now, let's wrap things up with some key takeaways about sentence transformers and their impact on NLP applications. One of the best NLP models for tasks like semantic search, retrieval, and text clustering, helping machine understand sentence meaning with high accuracy. They outperform traditional BERT models when it comes to sentence similarity tasks, making them better choice for embeddings. Fine-tuning gives you the flexibility to customize models for domain-specific applications, whether it's legal, medical, or technical content. If you need alternatives, OpenAI Ada provides a plug-and-play API solution, while MiniLM offers a lightweight and efficient approach for sentence embeddings. Sentence transformers deliver state-of-the-art embeddings, but selecting the right model variant and retrieval strategy is critical for optimizing performance in real-world applications.